This webinar will be held by Mattia and myself. I will talk in the first part of this webinar, I think around 20 minutes, more or less. And then I will give space and room to talk to Mattia that will show a case study that will try to explain with a real application of the methodologies that I will explain before. So the webinar will be about structural modeling and analysis, and particularly will focus on heritage buildings. How will as we will see, there are specific aspects of heritage buildings that needs to be taken into account when we analyze them. Let's start with the structural analysis. What is structural analysis? And to make it clear, more clear, I would start with some definition. So a model, these are general definition, a model and a simulation. A model is a set of entities and mathematical relationships that allow one to describe in a simplified and controllable form the phenomena that characterize a generally complex system. So in our case, the complex system is the building, subjected to some external loads. And we need to describe in the sense that we need to predict some outputs. The outputs more generally are the state of deformation of the building when subjected to these loads, because we know that whenever we have a structure, any structure, any object in reality, which is subjected to some loads, it reacts deforming, changing its shapes. And during this deformation, there is a state of stress internal to the building, internal to the body, that may lead eventually to collapse. The simulation is the implementation and execution of the model. So a simulation makes the model operational. In this sense, we will, while the model is the representation of the building, the simulation will give us the response. The response is, as I said, the state of deformation and the state of stress more generally. So in structural analysis, we identify basically three levels of modeling. We have geometric modeling, we have mechanical modeling or material modeling, and we have action modeling. I will briefly go through all these three levels of modeling. Firstly, let's start with geometric modeling. Geometric modeling is the part of this process of abstraction from reality to the mathematical representation, where we try to create an object that needs to represent as best as possible the structure under investigation. If we think of ordinary reinforced concrete buildings, which are the most common buildings that we have in our cities, we start from the very real building. We need to identify the structural parts. Structural parts, the structural skeleton, is the part of the structure which actually bears the loads. And in this case, they are the slabs carrying the floor loads. We've got the beams, the columns, walls, if any, structural walls, and foundations. So this is the geometric model, the structural skeleton of a reinforced concrete building. The further step is to create a model. A model, in this case, is a very simple representation where all these elements are represented by mathematical object, in this case elements, one-dimensional elements, which subjected to some loads can deform, and we can predict the deformation they have. Well, while for ordinary building, this is mostly straightforward and also well accepted in the research and in the professional community, historical masonry has many more issues that needs to be solved. Firstly, historical masonry, which is the represents the largest part of our historical heritage, may assume the form of a palace. Here you see Caserta Royal Palace, maybe a church, like in this case we've got the a church in L'Aquila in Italy, maybe a bridge, or maybe something, a part of the bridge but very complex, like vaults, columns, arches. So any of these elements are very different from each other and needs a proper representation, which cannot be something very schematic like the division in beams, columns that we have seen for reinforced concrete. And so for masonry, in particular for historical masonry, we have a plethora of different approaches to modeling, to geometric modeling. Here is some of them categorized into 4 elements. So we have into 4 groups. The first group refers to the most accurate representation, in which masonry is formed by blocks and mortar generally. So a binder mortar, and the block can be brick, can be stone, and so on. So the most accurate way of representing them is representing any elements in the mortar ensemble. So blocks and binder, and here is some approach of this case. There is a second level where we don't distinguish between the block and the binder, mortar and the unit. So we consider a unique material, and this is the continuum homogeneous model. Third type of approach is just to consider the geometry, because very often masonry structures think of a staircase like this, or a vault like this, works because of the geometry, because of the way in which the geometry is built. And so we have some geometry-based model. And finally, we have a last typology of modeling, geometric modeling, in which each part of the walls, in this case, are represented by specific elements. I think in this project, in the range project, we will focus on 2 main levels of modeling: the continuum homogeneous model, in which we have no distinction between block and mortar, and masonry is considered as a unique material, and the representation of masonry structure, or basically of each part, is made by means of solid and shell elements. There is another type of approach which was developed by Bartolomeo in particular, and its previous research group in Catania, which I think we will use in the representation of the case study in this project. Well, when we have a structure, so think of this church, we can create a geometric model of the structure, and to solve the mathematical problem, we need a way of transfer the external loads to the internal state of stress, state of deformation, how this building reacts to external loading. To do so, we generally consider a very small part of the material, a point that in the case of masonry is not a real point, but is a small ensemble of blocks and mortar. And we analyze the behavior in terms of stress and strain. So we perform some tests. We get a mathematical representation of the relationship between stress and strain. And when we insert this mathematical representation into the geometric model, we have a full model. There is another step, another part of modeling that we need to mention. But before getting to this, just a connection with wrench. In wrench, we have set an objective, which is the introduction of the effects of climate change on the material modeling of historical masonry. So this is the material modeling, mechanical modeling, the relationship between stress and strain will be an output of this project in the sense that we will try to insert the effect of climate change. So the effect of all the external situation like humidity, temperature, wind, whatever environmental action that will be affected by climate change can change the mechanical behavior of the single point, the small part of the structure where we have block and mortar. Finally, a quick mention of the action modeling, the third level of modeling. We've got, of course, several different types of loads that can act on a building. We got the dead load, so-called. The dead loads are the loads which are basically fixed in the structure, like the weight of the structure itself. We have the live load, which is a load, let's say the use of the structure, so people entering the structure or furniture and so on, all this type of generally vertical loading. We got earthquakes, we got blast. So we have several different types of loads, and all of them have a different representation, a different modeling. And just a note, we have a large uncertainty in the representation of the loads. Think of the live load. On a building, we can have one person, we can have 20 people, and this may change in the day, in the week, in the whole life of the structure. So in the definition of the action on the structures, we need to refer to the probability of an event, where the event is the loads on the structure. And we usually consider a combination of loads and a magnitude of the load, which has a certain probability of exceedance, we say. This is called fractile. Just a quick note, climate change is actually modifying the probability distribution of actions. Think of floods. Extreme floods are becoming more frequent, so the probability distribution of the flood loads is changing with time. However, this is not expected to be part of the range investigation, so we have not focused on this. Very quick part of this webinar is about heritage structure, why they are different from ordinary structures or new structures. There are some issues of heritage structures, not only masonry structures, but any kind of heritage structures. First of all, heterogeneity in the materials. So we can have very different materials because heritage structures have a long history of changes, modifications, and there was no standardization before the industrialization era, let's say. We have a lack of knowledge about geometry, materials, and loading history. And think of geometry, we don't have any documentation usually, or I mean, original historical documentation on how the building was conceived. And so we need to get to know our structure, and we have specific methodologies to do this. Also, past events may have modified the structural configuration. As I said, there could be enlargement of the building, changing. Think of the Ragusa church. Giuseppe has taught us that the dome was originally conceived in a way, but then because of time, and the time occurred between the design and the actual construction, the configuration of the dome changed completely. Also, past events in terms of loads may have changed the materials themselves by means of degradation, and also past events in terms of loads may have created damage on the structure, and we need to take this into account. Another issue is the difficulty of testing. So heritage structures are usually protected by institutions, and so we cannot perform destructive tests. Destructive tests usually are necessary to really understand the full, what we say, constitutive relationship. So the full relationship between stress and the strain. Strain is the deformation. So in the analysis of existing structures, we have a sort of analogy between what happens between doctor and patient and what we apply in the relationship between analyst and building. So there is a phase of anamnesis where we collect from the patient any information about what happened. And in the case of building, we collect any information useful for the diagnosis, the construction date, any events along the history, interventions, and so on. We have a phase of documentation when the doctor examines clinical documentation, and we have the same for the building. We need to examine available documentation, design blueprints of previous reports. We have a phase of visit. In the case of doctor-patient relationship, we've got a phase of visit when we inspect the building. We need to have a broader view on the building, its state, and we need to perform a survey of geometry to provide sufficient detail. Then we, of course, we got to investigate better by means of a plan of clinical analysis in the first case. In the case of an analyst-building relationship, we will prepare a test plan for materials and construction details, and then we need to examine these results. After that, we got to the diagnosis. The diagnosis is the assessment based on modeling and numerical evaluation of vulnerability of the building. So basically, we need to understand where are the weaknesses of the building and how we can, what are the limits for the loading application on our building. Finally, we have a therapy which is a plan of intervention. The same happens for a building if needed. So in the second part of this presentation, I will give room to Mattia that will explain all these phases with application to a real case study. This is a work that we performed. We are performing actually in these times. This is an activity that has started in the past but is going on. So I will give the word to Mattia.
Thank you, Corrado. Hello, everyone. I hope you see my screen. And I would like to show some application of the approach we can follow when we would like to assess the structural safety, let's say, of an historical building. And in particular, we will focus on the bell tower of the Church of San Michele Arcangelo, that is in Caserta Vecchia. Caserta Vecchia is an ancient village on the hill of the Caserta city in Campanian region, of course, in Italy. And this is a very interesting case study where we were very lucky to have a lot of information and also to perform some detailed analysis. So I think it's very interesting to use this as a benchmark case, let's say. So this is the church and the tower we are going to speak about. And the church was built in 1113, while the tower, the construction of the tower started about 100 years later, a century later. The church, the tower presents a total height of about 30 meters, and the prevalent material is the tough masonry that is very typical in this area. So, as Corrado said, we need to find some documents, some information, every kind of document it's possible to find for these structures. And in this case, we were able to perform a very detailed historical critical analysis and to recognize all the phase of the construction of the tower. And in particular, the tower experienced a lot of later interventions, and the current configuration is very different from the original one. For example, in 1782, the roof was destroyed and reconstructed in a different way. Also, how can you see here in this historical picture, the tower presented some lateral buttresses that were transformed by a very important intervention performed in the last century, which included also the introduction of an internal reinforced concrete frame. So this is a very singular case and a very interesting case study. We were quite lucky to find some historical document and also to recognize the actual configuration of this intervention, and also other later interventions that were performed during the last century, and in order to preserve the tower from some structural issues that experienced. After this first phase of anamnesis, we started with the visit part. No? So we performed some geometrical survey, and in particular based on US photogrammetry, which allowed for obtaining a very detailed geometrical survey, and in particular of the structural part of the tower that were then used to realize some structural model. Also, we performed some analysis, some investigation in order to understand the state of conservation of the tower. And this was performed by using some thermal camera that give us information about the external temperature and the eventual presence of some degradation phenomena. Also, we performed some investigation on the tower in order to verify that the information based on the document we found were confirmed by the real configuration of the tower. And so here you can see some non-invasive investigation we performed inside the walls of the tower in order to check the presence of this reinforced concrete frame inside the tower that, of course, it's very, let's say, change the behavior of the tower under different kind of loads, and of course also in terms of possible degradation phenomena due to the climate change. Then the investigation was completed by a very accurate dynamical characterization of the global behavior of the tower. So we put some instruments in specific point of the tower. We recovered some acceleration, some displacement of these points, and by means of some elaborations, some mathematical elaborations, we understood how the tower behave under external loads, and this is actually called operation model analysis that give us a very interesting information in order to calibrate numerical models and to perform the structural assessment of the tower. Structural assessment that, of course, included both the masonry part and also the reinforced concrete part, and was performed by means of finite element analysis by adopting the macro modeling approach that Corrado discussed before, and allowed us for performing some seismic analysis. And in this case, for example, we simulated the presence of an earthquake by applying some acceleration at the base of the tower. Corrado, if you want to conclude with the ongoing activities.
I would like to show you some first images of the trip that we had last week in Ragusa, where we started these activities on the church. So on the right you see Mattia doing material testing, non-destructive material testing to identify the structural configuration of the columns and the main material of the blocks, and some moments where the other researchers that were with us, Domenico and Rosina, were performing a geometrical survey of the structure. Our aim in this project is the dome that you see on the right, but yes, this will be while the dome was surveyed. Of course, it was inaccessible for material testing, so we need to extrapolate information from the church to the dome. or better, in the future we will be able to perform some material tests when we could go, if we could go to the dome directly. And this is just the beginning. Thank you. I think we can close this webinar.